Hello everyone. I would like to welcome you to this tutorial, Analysis, Simulation and Implementation of Vector Control in Extremely Low Cost Laboratory by myself, Ned Mohan, and Dr. Siddharth Raju, my colleague. So this is a great opportunity for both of us to be able to present this tutorial. And I would like to give you a brief background of myself. I did my PhD at University of Wisconsin-Madison in 1973. And then I came to the University of Minnesota at the end of 1975. And that's where I have been doing research and teaching. And then what I'll do is present just a few slides in the beginning and a few slides at the end, and I'll let Dr. Siddharth Raju to cover the rest of it. So just as a brief outline, we have this consortium of universities for sustainable power, CUSP. So I'd like to give you a little bit background about that. And then I will let Dr. Siddharth Raju talk about all the rest of the sections, and I'll say a few things at the end. So the bottom line is that this tutorial is designed to, present analysis from the very basic electric machines to drives, and then also their simulation, as well as taking it to controlling machines and drives in the hardware laboratory. So I'll move on. So I'd like to give you a little bit of background on this consortium for sustainable power. And so this consortium has, if you click on this button over here, this tab over here, it has 235 US universities as members, and it has a number of courses that have been uploaded. So if you look at electric machines and drive-related courses, we have these 4 courses. Actually, there's one coming. This is not listed here, but you can see the basic course is over here, and then the control course is right here, vector control. And there's a course on electric machine design by by Jim Hendershot, and then there is a course on FEA, using FEA for machine design by Professor Jonathan Bird at Portland State University. So, and you can see by going to these courses that they are pretty complete, in terms of student learning objectives and all the slides that a instructor may need, and also the videos for every lecture. So these are as complete as we could make them, and we are very grateful, as I'll say later on in the acknowledgement, for the grants that we have received from Office of Naval Research here. So these are the list of courses that we have developed over the years, and these courses are not all developed at the University of Minnesota. Because of these grants, we were very fortunate to reach out to experts in their respective fields all over the world. So with their help, we have developed these courses, and some of them, actually most of them, are full semester courses. So we are dreaming that at someday, using these courses, we may be able to organize a master's degree. So, that is still in the planning stage. Okay. So these courses are based on textbooks, so that you can think of them as a foundation for these courses, in order to follow these videos and slides that I showed in the earlier 2 slides. One doesn't need to buy these books, but nevertheless, they are available. So they are printed by Wiley, and this one is on power electronics here. Okay, first course in power electronics. This is basic electric drives. So here, basically, we talk about electric machines in steady state, but in such a way that that analysis seamlessly leads to this vector control. Okay, so these analysis of these machines in these two courses is more physics-based. Okay, at the end of the day, you have to write the mathematical equations in order to be able to simulate these machines. But they give a sort of a basic idea as to how they operate, okay, on the physics basis here. So what has happened recently is that taking all these three books that I showed you in the earlier slide, they have been combined into a new book here, and it just was recently published. So it has been published, so you can go to Wiley website and you can get the link for it. The instructor website is still being developed as we speak. Okay, so the difference between the books over here and this book here is that in this book, we not only have simulations in MATLAB Simulink, but we also have simulations in so-called Sciamble Workbench that Dr. Siddharth Raju has developed. And you know, if you simulate these machines and drives in that software platform, then it seamlessly leads to controlling of these machines and hardware. Okay, so that's the beauty of it, and this machine and this book combines all that, and we hope to give that impression in this tutorial. Okay, thank you so much, and I'll hand it over to Siddharth.
Hi, I'm Siddharth. I'm a researcher at the University of Minnesota in Professor Edmond's laboratory. Before I dive into the topics that Professor Mohan had outlined earlier, here is a brief demo that encapsulates the goal of this session. Here is the overall induction motor vector control model. We will go over the details later on in this session. We have an induction motor under speed control and a coupled DC generator to emulate a load under torque control. The system is modeled using Sciamble Workbench, which can be used to directly control an actual power electronic hardware in real time. The motor speed data is logged back in real time as seen here. The motor speed remains constant at 100 radians per second, even when a step load torque of 0.1 Newton meter is applied. In this session, we will break this complicated system into smaller parts and understand the underlying structure and reassemble it to implement an induction motor and permanent magnet synchronous motor vector control on an actual hardware. Throughout the session, we will be using Sciamble Workbench for all the simulation modeling as well as real-time control. So what is Sciamble Workbench? It is a numerical simulation software similar to other commercially available platforms such as Plexum, Vissim, PSIM, MATLAB, etc. It allows users to build complicated systems using pre-built simple drag and drop toolboxes. For systems that cannot be modeled using a model-based environment, the software also offers an advanced coding environment which supports inbuilt matrix operators. Workbench started as a lab development project for power electronics and motor controls. We evaluated various off-the-shelf solutions and found them unsuitable for our application for different reasons. The commercially available platforms such as Simulink, Plexum, PSIM, Vissim, etc. are expensive even for academic users and are exorbitantly costly for non-academic users. The free options such as Scilab does not support device-specific code generation, as well as their UI are extremely primitive. The final option is to directly program the control system in native C language rather than using model-based design environment to generate the code. There are various platforms available such as Code Compose Studio for TI devices, MPLAB X for microchip devices, and all of these have the same issues that it requires the user to have significant knowledge about the device architecture as well as significant programming experience. To overcome these shortcomings, we developed our own numerical simulation and real-time code generation platform, Sciamble Workbench, that is shown here. We'll go over the different aspects of Sciamble Workbench that differentiates it from other platforms in the next couple of slides. One of the interesting features of Workbench is the dynamic error and warning reporter that is supported by the incremental compiler that runs in the background of all Workbench application. It reports any error or warnings instantaneously as and when they occur rather than waiting till compile time. This significantly cuts down on the design time and accelerates any design process. As mentioned earlier, in addition to the model-based environment, Workbench also has a code-based environment that supports dynamic compilation. It is extremely easy to use and highly intuitive language with support for inbuilt matrix operators. The Workbench software also supports real-time code generation, which is of most interest to us for this particular session. In Workbench, a single model can be used in both simulation as well as real-time. The model can be transitioned from simulation to real-time by just a single click. Here is a model of an induction motor vector control. This is the mathematical model of an induction motor, and on the bottom we have a mathematical model of the DC motor. To the left of the motor model is the induction motor vector control PA controllers, and to the left of the DC motor is the PA controller for controlling the load torque. And on the right of the induction motor we have the current sensors and the speed sensor, and the right of the DC motor we have the DC motor current sensor. In simulation mode, all of these models are compiled and run, and the results are shown in the scope. With a click of a single button, the model can be transitioned from simulation to real-time, as seen here. In the real-time mode, an intelligent algorithm running in the background will automatically identify that the induction motor model and the DC motor model needn't be compiled and converted to real-time C code, because these are actual motors that are connected to the power electronic unit, and hence they don't need to be programmed in real time. The device settings are shown on the left, and as can be seen, the user does not need any knowledge of the device registers to be able to configure any particular device. In addition, the software is completely device agnostic. That is, if you're using one particular microcontroller today, you can transition to another supported microcontroller later without having to modify the model in any way. In the next 1 hour of this session, we should look at developing a DC motor model and the control algorithm necessary to control this motor in a real-time environment. Before we do that, let's look at the reason as to why we need an electric drive. Here is the breakdown of the energy usage. Here is the breakdown of the energy usage in different sectors in the United States during the year 2013. US consumed approximately 96 quads of primary energy that year, and 32% of it was consumed in the industrial sector, and a combined 39% was consumed in the commercial and the residential sector. Here is the breakdown of the percentage of energy used in different applications in the residential sector and that of the commercial sector. For both of these sectors, the major component of energy is spent in ventilation. Currently, most of these systems use direct line connected motors, and there is significant energy saving potential by means of motor upgrades as well as using variable speed technology. In the residential sector alone, there is a potential to save about 0.54 quads due to motor upgrades and using variable speed technology. And similarly, in the commercial sector, there's a combined potential to save about 1 quads. This comes to about 3.76% of the total electricity generated in 2018 in the US. That is a significant amount of energy saving by just doing motor upgrades and variable speed technology. In addition to the significant energy saving potential offered by electric drives, they also enable torque, speed, and position control of the motor in spite of changes in the load conditions as shown in the graph below. Electric drives have 4 major components: the motor being driven by a power processing unit, which is controlled using a digital controller based on the signals read by a sensor, which is sensing either the motor currents or the speeds. The most commonly used structure for power processing unit is shown in the slide. On the left is a full bridge converter that is commonly used for a DC motor drive, and on the right is a 2-level 3-phase inverter that is used for both induction motor as well as permanent magnet synchronous motor drives. To understand the operation of these converters, let's initially start off with a simple switching power pole. The input of the switching power pole is an uncontrolled DC voltage VD. The control voltage VC is compared with a high frequency carrier to generate a modulation signal for the switching power pole to produce a desired output voltage VAN. When the control voltage is greater than the carrier voltage, the switch is turned on, connecting the output voltage to the DC bus. Thus, the output voltage is equal to VD. And when the control voltage is less than the carrier voltage, the switch is turned off, connecting the output to the negative of the DC bus, thus setting the output voltage equal to 0. The average of the output voltage can be controlled by modulating the ratio of the on and off time, which is in essence controlling the duty cycle of the power pole. The average output voltage over one switching instant can be shown to be equal to the duty cycle times the input DC bus voltage. The output of the switching power pole is connected to an inductive element. Thus, even though the voltage of the switching power pole is pulsating, the current through the inductor would be smooth. The half-bridge converter that we saw earlier is a unipolar converter capable of generating output voltage only between 0 and plus VDC. To enable the DC motor to rotate both in clockwise as well as counterclockwise direction, it is essential that the voltage generated by the converter be bipolar. To do this, we use a full bridge converter, which is an extension of an half-bridge converter that is obtained by adding an additional switching power pole to the existing switching power pole of a half-bridge converter as shown in this image. To generate a positive output voltage, switch A is connected to the positive DC bus, while switch B is connected to the negative of the DC bus, thus setting the output voltage equal to positive VD. And to generate a negative voltage, the switch B is connected to the positive of the DC bus, while switch A is connected to the negative, thus generating minus VDC at the output. And modulating the duty ratio as we did for the half-bridge converter, the magnitude of the output voltage can be varied all the way from plus or minus VDC. It must be noted that there is no constraint on the waveform of the control voltage VC. So the same drive can be used to generate a sinusoidal single-phase output voltage as well, by simply adjusting the control voltage to follow the profile of a sinusoid. The full bridge converter can be extended to a three-phase two-level inverter by adding one more switching power pole to the full bridge converter, as shown in this image. Instead of using a constant modulation signal as was the case for DC drive, we can adjust the modulation signal to follow the profile of a sinusoid to generate sinusoidal output voltages. The magnitude of the control voltage for all three phases are maintained the same, while their phases are shifted by 120 degrees to generate a balanced three-phase sinusoidal output voltage. This concludes the basic power electronics knowledge that is necessary to implement a DC motor speed control drive. To model the DC motor in Workbench, we first need to convert it into a transfer function form. To do that, let's first revisit some of the basic equations of a DC motor drive. On the left shows the magnetic circuit of a DC motor. In this particular case, the stator is a permanent magnet and the rotor is an electromagnet. The rotor consists of the armature winding that is evenly distributed. The commutator brushes ensures that the flux established by the current in the rotor windings is always along the direction of the flux established by the stator permanent magnets. The image in the middle shows the equivalent circuit of a DC motor. The equations on the bottom can be easily derived from this equivalent circuit. The first equation is the terminal voltage is directly equal to the drop across the armature resistance and the inductance and the back EMF. By Faraday's law, the voltage induced across the armature winding is going to be directly proportional to the rate at which the flux changes in the winding. Hence, the back EMF is directly proportional to the speed of rotation. The flux produced by the currents in the armature winding interacts with the flux established by the stator magnets to produce electromagnetic torque. Thus, the electromagnetic torque is directly proportional to the current in the armature winding. And in SI units, the torque constant Kt in this equation is equal to the back EMF constant Ke in the previous equation. The final equation is for the mechanical system, which is inertia times the rotational acceleration is equal to the differential torque experienced by the rotor shaft. The rightmost graph indicates the speed versus torque characteristic of a DC motor. As can be seen, when the rated voltage is applied and there is no load torque, the motor spins at rated speed. But as more and more load is added on to the rotor, there is going to be increased current demand because the torque is directly proportional to the current. And this increased current demand is going to drop more and more voltage across the series armature resistance that is going to lead to reduced back EMF, which in turn is going to lead to reduced speed because the speed is directly proportional to the back EMF. Thus, as can be seen, as the rotor is loaded more and more, the speed of the DC motor drops gradually. In addition, as the terminal voltage changes, the speed of the motor changes as well. Thus, as can be seen, a direct line connected DC motor cannot be maintained at a constant speed under varying terminal voltage and load conditions. The electrical equation can be rewritten in the transfer function model as shown here, and the mechanical equation can be rewritten in transfer function model as shown on the right. The electrical system and the mechanical system are coupled together by basic Maxwell's equation, which relate the back EMF to the speed and the torque to the current. This overall transfer function can be drawn as shown in the figure below. The difference between the input voltage and the back EMF is passed through the 1 by SL plus R transfer function to obtain the armature current IA. The armature current IA is scaled by the torque constant KT to obtain the electromagnetic torque. The differential torque is integrated by 1 by Sj to obtain the motor speed omega m, and omega m is scaled by Ke to obtain the back EMF. So this completes the loop where an applied terminal voltage would generate some particular speed based on the load torque that's applied. So let's implement this model using Workbench. For anybody who is interested, you can follow along by visiting this website. Workbench is absolutely free of cost. Anybody can download it irrespective of academic or commercial purpose. You can download it and just follow along to implement this model. So let's go ahead and run this model. Just to save time, I have a pre-made model that I'm going to use for this demonstration. But as I mentioned earlier, you can follow along the link to build this model from scratch on your own as well. So here is the DC motor model that we saw earlier. So we have an input voltage VA. We subtract the back EMF, pass it through 1 by SL plus R. In this instance, we are using 5.2 millihenry for the inductance and 2 ohms for the resistance. And the output of this transfer function is going to be the armature current. And you scale it by the torque constant, and that would give you the electromagnetic torque. In this case, we are using a torque constant of 0.1. And when you integrate the differential torque by 1 by Sj, and in this case, we are using a moment of inertia of 150 micro kg meter square, the output of this block would be the motor speed omega mech, and you scale the omega mech by the back EMF constant Ke, you'll end up back with the back EMF voltage. And as I mentioned earlier, in SI units, Ke would be equal to Kt. There is a back EMF constant the same as the torque constant. And this will not be the case if any other units are used other than SI units. So let's go ahead and run the system. We are using just a simple Euler solver, and we'll use a very moderate step time of about 0.1 millisecond. So let's go ahead and run this model. So we have our input voltage, and we can look at different parameters in this window. So we have an input voltage that is initially 0, and at 0.2 seconds, we are stepping the input voltage to 10 volts. And we have an initial load of 0 Newton meter, and at 0.6 seconds, we are stepping the load from 0 to 0.1 Newton meter. So if you look at the speed, so the speed is 0 because initially the voltage is 0. And at 0.2 seconds, we applied a voltage of 10 volts, and the speed ramps up to about 100 radians per second. And at 0.6 seconds, we applied a load torque. And as you see, the speed drops because we added a load torque that is going to lead to increased current. That's going to lead to drop in the armature resistance in steady state, which then is going to lead to reduced back EMF, which in turn is going to lead to reduced speed. So that's why we see the speed drop. And this would be a problem if you're expecting the motor to run at a constant speed without any control algorithm, because as soon as it's loaded, the speed is going to change. So let's go ahead and look at the current profile. Before the voltage is applied, the current is going to be 0. And as soon as the voltage is applied, the motor is accelerating. There's going to be a d omega dt component, which in turn means there's going to be a torque component. So there's going to be an electromagnetic torque, which in turn is going to cause some current in the armature winding, because the armature current is needed to produce the torque. And that's the reason you see the current spike. But once the motor stops accelerating, once it reaches steady state speed, you see the current die down to 0, because there's no more need for torque, and hence the current is not going to be produced. This is only going to happen in simulation. In reality, there's always going to be some residual current because there's going to be a frictional component. We could have modeled the frictional component as well by, instead of using 1 by Sj, we could have used 1 by Sj plus B transfer function, where B would be the viscous friction because of air. If we had modeled that, there would be some residual current even in steady state under no load. But at 0.6 seconds, once we apply a load torque, you can see the current increases proportional to the load torque. We had a KT constant of 0.1 and torque of 0.1 Newton meter divided by KT, which was 0.1, the current would settle at 1 ampere as seen here. So this is a very simple simulation of a DC motor. Let's go ahead and now try to add controller to it so that the speed always remains a constant irrespective of what the load torque is going to be. So these are the results again. So we are going to be using throughout this session a simple PA controller for all the control algorithms. There are other algorithms which have various advantages and disadvantages, but for this session we will simply stick to PA controllers. Traditionally, there would be a D component involved in most P controllers, becoming a PID controller, but we will avoid a D controller because, as we will see, all of our measured signal would have a significant amount of noise. And wherever there is noise, we use a differential controller. The differential controller is going to amplify the noise, which is going to completely mess up with the algorithm. So in any real world implementation, before you use a differential controller, you'd usually have a filter that filters out the noise signal, or you would restructure your algorithm in such a way an integral and a differential component cancel out. You rewire your control algorithm so that differential and an integral component cancel out so that you don't end up differentiating an input signal which can be noisy. So what does a PI controller do? You have a reference signal and you have a feedback of that signal that's measured. For this case, we are measuring the speed of the motor. This is the reference speed that we want. Let's say we want the speed to be 100 radians per second, and we are measuring the speed, and the speed is at 90 radians per second. So we find out the error signal, the difference between the two, it ends up being 10 radians per second. And we proportionally gain, let's say we have a gain factor of 1. So we end up applying 10 times 1, we end up applying a voltage of 10 volts so that the motor starts to accelerate. And as the motor speed increases, let's say it comes to 95 radians per second, the error reduces, it becomes 5. The motor applied voltage also reduces to 5. So the rate of acceleration reduces. So the motor becomes slower and slower until it reaches 100 radians per second. And the problem with just using a P controller is as soon as the speed reaches 100, the error component would become 0, which means the applied terminal voltage would end up being 0, which means if there is any frictional component, which there would be in any real world application, or there's any torque loaded on the rotor shaft, the motor would start decelerating because there's no longer voltage applied on the terminals. So the motor is going to start to decelerate. So the voltage can never be maintained at 100, the desired voltage, if you're using only a KP controller. To overcome this, we use a PA controller as well, which is a memory element. So whenever there is an error, it will integrate the error to produce some output voltage. So even when the error goes to 0, this integral element is going to maintain whatever the last previous state was, since it's simply a memory element. So even though the error went to 0, the voltage could be maintained at say 2 volts to sustain the required load torque or the frictional component. So that's why you use a P and an I proportional as well as an integral controller for motor control applications. And the transfer function of it is pretty straightforward. You have Kp plus Ki by S, and it can be rewritten in this particular form. We can cascade these controller in multiple stages. So we had a speed controller directly producing an output voltage. But in most practical applications, it would be cascaded design, where you have a speed controller, the output of which would be a desired current. And then there would be another PA controller, the output of which would be the desired voltage. This kind of cascaded control allows you multiple level of transient control. So you would have an inner controller which controls the torque and an outer controller which controls the speed. We'll look at further design detail of these controller in the next few slides. So we'll design the speed controller assuming that the inner current loop controller or the inner torque controller is ideal. And similarly, we can add one more stage to the controller. If you want position control instead of speed control, we can add an additional cascaded layer of a PA controller with input being the reference position followed by the reference speed followed by the reference current. It must be noted that when we have say 3-stage cascaded control with position being controlled, we cannot control the steady state speed and we cannot control the steady state current. There is only one control variable, which is the terminal voltage. Thus, you can only control one particular parameter using the terminal voltage. But what this cascaded control stage allows you to do is control the transient waveform of both the speed and the current, even though you can only control the steady state position and not the steady state speed and the current. So let's go ahead and design a current controller to control the armature current of a DC motor. So this section is the motor model that we have already modeled using Workbench. We have the 1/SL plus R transfer function that converts the difference in the terminal voltage and the back EMF to current. And then you scale the current to get the electromagnetic torque, and you integrate the differential torque by 1/Sj. You would get the speed, and the speed you scale by back EMF constant, you'll get the back EMF, and that will close the loop. So this part is already known. This is the model for your PWM converter. And for all our simulations, we'll assume that it's just a simple gain, a unity gain. That is, our power converter is ideal. Whatever required voltages, it's going to be generated as the output. And we have the PA controller, which we saw in the previous slide. So we have a reference input current. Say we require a current to be, armature current to be 5 ampere. It's going to measure the motor current. And depending on what the current is, if it's going to be less than 5, it's going to generate a positive error, going to generate a voltage that's going to make the current increase. Or if the current is more than desired, it's going to generate a negative error that's going to generate a voltage that's going to reduce the current. So the transfer function can be restructured by juggling the components around as shown here, and can be further reduced as shown here. It must be noted that the reduction from this stage to this stage is solely possible because the time constant of a mechanical system is orders of magnitude than the time constant of the electrical system. So in the mechanical system, we ignore the viscous friction, but if you assume the viscous friction as well, you would have 1/Sj plus B as your mechanical system transfer function, and your electrical system transfer function is going to be 1/SL plus R. So the time constant of the electrical system is going to be L by R, and the time constant of your mechanical system is going to be J by B. And if you look at this, for most practical motors, your J by B factor is going to be orders of magnitude higher than L by R. So your mechanical time constant is way higher than your electrical time constant. What this basically means is that any transient in the electrical system would have settled down and reached steady state before the mechanical system can observe it, or the effects are felt on the mechanical system. So this is what enables us to reduce from stage 2 to stage 3, where we ignore the mechanical components in the above transfer function. So with this reduced form, the transfer function can be returned. For the system, transfer function can be returned in this form shown here. We have the PA controller followed by the power processing unit, which we would assume throughout the session to be a unity, and followed by your motor model. If you're modeling an actual converter, this would not be unity because there's going to be some dead time in the switches, which is going to reduce the amount of modulated output voltage, and there are going to be other nonlinear effects coming into the picture, which we will ignore for this session. So this is your overall system, and we need to tune this KPKI values so that we get some desired response in the output. Here is the open loop Bode plot of the reduced transfer function from the previous slide. Our aim is to design a controller that's stable under all operating conditions and has certain desired properties in terms of the rise time and settling time, as well as the oscillatory nature. The objective of the controller is to make the motor current follow the desired profile, and how faithfully this reference is followed can be controlled by adjusting the phase margin of the system and the crossover frequency. Adjusting the phase margin enables us to adjust the profile, response profile, for a step input change. So if the phase margin is very close to 0, the profile is going to be, the response is going to be very oscillatory in nature. And if the phase margin is farther away from 0, closer to 90 degree, the response is going to be more overdamped in nature. So controlling these two, controlling the phase margin, you can easily control the response, the characteristic of a response of a first order transfer function, which is the case here. The choice of crossover frequency is usually limited by the switching frequency and the minimum requirement of the control bandwidth for a speed controller. So for example, consider your switching frequency is 6 kilohertz So consider your converter as a switching frequency of 6 kilohertz. Then a choice for your crossover frequency for the current controller could be 600 hertz, 1/10th of it. This is just a thumb rule. It could be 1/10th, 1/4th, 1/2, but it definitely can't be greater than 1/2 because of the Nyquist criterion, but it can be anything below that. And depending on how responsive your system needs to be, you can select this particular frequency. And closer you get to your switching frequency, there's going to be more switching frequency component being corrected for by the controller, which might not be beneficial, which could cause a lot of harmonics, which could cause a lot of oscillation in your motor torque. So you would preferably go to as low as possible a frequency for your crossover frequency. The lower range would be limited by any cascaded controller that you have prior to the current controller. So say the current controller is preceded by a speed PI controller, and the crossover frequency for that PI controller would by thumb rule be 1/10th of this frequency, the inner current bandwidth. So that would be, say, 60 hertz. And if this is within your design requirement or satisfies your design requirement for your speed loop bandwidth, then this would be absolutely fine. So you would usually start off with a design requirement. Say you want your motor speed bandwidth to be as responsive to up to, say, 50 hertz or 100 hertz, whatever it be. So this would set your lower limit for the bandwidth for your speed controller, and in turn the lower limit for your crossover frequency as well. And that in turn will set the lower limit for your current controller crossover frequency, and in turn the lower limit for your switching frequency. So this goes hand in hand, the lower limit for your mechanical requirements as well as the upper limit for your switching frequency. This would determine what omega C would be for any practically designed systems. So how do we design the PA values for the speed loop? We assume that the inner current control loop to be ideal. This is again a very reasonable assumption, given that your electrical transfer function has a time constant that is much, much lower than your mechanical time constant. In addition to it, you are putting a controller on top of it, which has a higher bandwidth than your speed controller bandwidth. So for all practical purposes, you can assume that any change in the reference current would reach steady state before your speed reaches steady state. So for instance, say you have a step reference change in the speed, and you have a profile that goes along like this. If you look at the inner current speed, say it also had a step reference, it would be at a much, much higher speed. The profile or the time for it to settle would be much lower compared to the time for the speed to settle. So that enables us to assume that the inner current control is just a unity gain block. So all that remains in the motor model is your KT, your torque constant, and your 1/SJ, your mechanical system. And the output of which would be the speed, and the difference between this would be fed to the PA controller. So the design for this is same as what we would do for your PA controller design for your current. You have a similar transfer function model, and you choose a KPKI value for desired phase margin and the crossover frequency. So these two equations can be solved. You have two variable KPKI. So it's pretty straightforward equation to solve. It is a nonlinear equation, but you can substitute KP from this equation into the first equation to solve Ki, and then resubstitute to get KP. So this is the open loop transfer function, open loop Bode plot that we saw earlier. And the closed loop Bode plot is pretty obvious. It's expected to be of that of a first order system. So what we want is, until the crossover frequency is reached, we want whatever input to be reflected as the output. So say you want a reference current, you have a reference current of 10 ampere. You want your control system to be work as if it's a unity gain block, so that the output is also 10 ampere. So if you have a reference current of 10 ampere, your motor current should also be 10 ampere until you reach the crossover frequency. So that is what is indicated by magnitude of 0 dB, which means a gain of 1. And after the crossover frequency, you want a very steep roll off, which is 20 dB per decay, which is for a first order transfer function. So what this basically means is, if you have a step in current from 0 to 10, you want any transient that is caused because of the step to rapidly roll off and settle down. So this is your reference current, and say this is your output current. You want this transient to rapidly settle down to the desired value again, which is 10 ampere. So the rate at which it settles down is going to be controlled by the rate of fall of the Bode's magnitude plot. And the second plot is the phase plot. So again, as long as it's within the crossover frequency, you want the phase of the system to be absolutely zero. So whatever is in the input is reflected at the output. So that means, say, if I have a very low frequency sine current that is desired to be generated, the output would still be the same low frequency current with a magnitude of 10 ampere. And the phase difference between the reference current and the actual current would be zero at very low frequencies. And once you reach high frequency, this is the low pass system. The closed loop system is effectively a low pass system. So it is going to reach phase minus 90 degrees. So let's go ahead and design this PA controller in Workbench for the simulation model. Then we'll go ahead and run it in an actual hardware as well. So as I mentioned earlier, you can follow along. Just go and visit this link. It has step-by-step procedure to recreate this model from scratch. For lack of time, I'm going to use a pre-built model for this demonstration. Let me go ahead and open Workbench. Let's go to part 2. So all I've done is I've moved the DC motor model that we had designed in the part 1 into a subsystem. And I have added a PI controller for the current loop. So we have the KP value, KA value, and you have the integrator for the integral part of PI. And I sum the KP, KI. So this is KP, and then you have KI by S, so sum of this. If it is only simulation, we don't need the saturation block. In simulation, this control voltage can vary from any value, but we will use the similar model in real time as well, where there is a limited voltage that can be generated. We will use a DC bus voltage of 40 volts in our real world application. We are going to use an inverter, which has a bootstrap capacitor, which means we cannot get absolute 40 volt at the output. So there's going to be a minimum dead time that's required for the bootstrap circuitry to work, which is going to limit the amount of voltage that can be generated at the output. In addition, the switch is also going to have some voltage drop, so that further reduces the amount of voltage that we can generate practically in an actual inverter that we are going to be using next. So we are going to set the saturation at plus or minus 38 volts. And similarly, the integrator also needs to be saturated. If we don't use an anti-wind-up in the integrator, we would end up having sustained oscillation due to the nonlinear limit cycles that will be introduced. So that is the inner current PI loop. So we have a reference current and we measure the actual current, and the error is going to generate, go to the PI controller, which is going to generate a control voltage, which is going to adjust the current so that the actual current matches the desired current. This is cascaded by a speed PI controller. Again, the speed PI controller takes the reference speed and the measured speed. The error is going to generate reference current. And this current is going to get connected to the inner PI controller. So say your measured speed is lower than the reference speed, the current is going to be positive current. That means a positive torque, which means the motor is going to accelerate and the speed is going to catch up to the reference speed. And if the speed was greater than the reference speed, that means there's going to be a negative error, which in turns mean negative current, which in turns mean negative torque, which is going to decelerate the motor so that it converges towards the reference speed. And once again, we're using the same Euler solver, and we're using a step time for the solver of 0.1 millisecond. And the KPK values are basically used from solving the two equations that were shown in the previous slide. The procedure to solve this is also available on the link that was posted in the slide. So let's go ahead and simulate this. So what we have is at 0.1 second, we have a step in the reference speed from 0 to 100 radians per second. And at 0.6 second, we increase the load torque from 0 to 0.2 Newton meter. In our previous simulation, what we saw was when we increased the load torque, the speed dropped. But in this case, since we have a PA controller, even when we increase the load torque, the speed is remaining at 100 radians per second. It is going to have a transient drop, but then the PA controller is going to correct for it and bring it to the steady state speed. Once we have a step change in the reference speed, you see the PA controller adapts to it and brings the steady state speed to the reference speed. If we look at the current, when the motor accelerates, you're going to have some steady state current, you're going to have some current, and once the motor settles down, the current dies down to zero, and there's only going to be a residual component of current. In our previous simulation, the residual component went to 0 because we didn't use frictional component. In this case, we're using a frictional component as well. So we're using 1 by Sj plus B. So there's going to be a residual current to sustain the viscous frictional component as well. And at 0.6 seconds, we load the motor with a load torque, and you see the armature current increase proportional to sustain the load torque in addition to the viscous friction component as well. That's the simulation for DC motor closed loop speed control. So let's go ahead and look at the simulation model for, let's go ahead and implement the same thing in hardware as well. So here is the hardware model that we'll be using. We have a three-phase inverter, three-phase inverter here. We'll just be using 2 phases. There is a full bridge converter. In simulation, we just used a step toolbox to simulate a load. But in reality, we have an actual generator which is running in torque control to emulate a load torque. On the right, we have the DC motor, and you have the encoder going back into the inverter module. And this inverter module has a controller on board, which measures the speed signal as well as the motor currents, implements the PA controller on board, and generates the desired voltage that is then fed into the motor terminals, which in turn controls the motor speed. The details of this inverter module will be visited by Professor Mohan at the end of the session. Let's go ahead and run this model in hardware. So here is a motor model. Let me go ahead and open it in Workbench. That would be part 3. Once again, anybody can follow this. If you have the actual motor, the inverter module with you, you can follow along this experiment. And you can get the inverter module by visiting, if you go to Sciamble.com, in the resources, in the product section, there is the electric drives lab kit that has all the inverter module as well as all the motors that you can obtain and just try out these experiments yourself as well. So here is the model. I have removed the DC motor model since we are going to do it in real time and we have actual DC motor. But as I mentioned earlier, you can have a single model in Workbench for both simulation and real time. Just to keep the model simple, I have removed the DC motor model. So on the top here, we have the inner current control PI loop and the outer speed control PI loop. And we are measuring the speed feedback from the motor and an encoder connector on the motor. And we have all current sensors on board, which we are using to measure the currents. And we generate this reference output voltage using a full bridge converter. And the duty cycle for this full bridge converter is generated using the formulas that we had shown in the slides before. To emulate the load torque, we have a DC generator that's coupled, and that is run in torque control mode or effectively current control mode because torque and current are proportional in a DC motor. And both of these inverters are enabled. So let's go ahead and run this motor. Before I run it, here's a view of the actual hardware. Here is the hardware setup that we are going to be using to implement the DC motor speed control in real time. On the right, we have a DC motor that has a rating of 42 volts and 5 ampere, which we are going to be running in speed control. And on the left is a similarly rated DC motor that we are going to be running in torque control mode to emulate a load torque. The speed of this coupled motor generator set is measured using a 2048 line A quad B encoder, and the data is fed back into the controller on board the inverter on the top here. The inverter is rated for 50 volts, 10 ampere operation. Here is what's inside the inverter module. It consists of 3 3-phase inverters that enables us to run a doubly fed induction generator under vector control, in addition allowing us to control a coupled motor as well to emulate a load. This inverter also has a controller on board that allows us to implement all of the control algorithms digitally. The onboard programmer and the data logger allows any model developed using Workbench to be directly programmed into this controller, and it also allows us to vary any data on the microcontroller in real time from Workbench and also measure and log any data from the microcontroller back onto Workbench through USB connection. Let's go ahead and run the system in real time. We are using a standard 42 volts 5 ampere DC power supply to power the inverter module. Once we press the run button, Workbench compiles this model into native C code and programs it onto the onboard microcontroller. And Workbench does not require any additional third-party softwares to accomplish this task. All the speed and current signals measured by the microcontroller is logged back into Workbench in real time and can be viewed using the scope that we had used to see simulation results as well. So here is the speed data being read back in real time. And as you can see, at time equal to 1 second, we applied a step in the reference speed, and the PA controller rapidly compensates for the change in the reference and brings this motor speed to 100 radians per second as well. And at 7 seconds, we applied a load torque, and thus the motor speed dips a little bit, but the PA controller recovers quickly and brings the speed back to 100 radians per second. And if you look at the current feedback, before 1 second, when the step in reference speed was applied, the motor current is 0. And once we apply a step in reference speed, as the motor accelerates from 0 to 100, there is going to be a need for electromagnetic torque, and thus there's going to be an armature current as well. And once the motor settles down to about 100 radians per second, as we saw at about 1.5 seconds, the motor current also settles down to a residual current that is needed to satisfy the torque demand due to the viscous friction. And at time 7 seconds, we applied a step in the load torque of about 0.1 Newton meter, and our KT value or the torque constant was 0.1. So the net increase in the current is about 1 ampere as seen here. There is significant amount of noise in the measured current signal since the current sensors are placed right at the output of the switching node. This was the reason in our controller design we did not have a D controller or a derivative controller, because a derivative controller, by differentiating its noise, is going to merely amplify it and mess up with the control algorithm. So let's stop the inverter and look at the device properties that I briefly mentioned earlier. And as you see here, we are running the inverter at 24 kilohertz and we're using a triangle carrier for the PWM generation. The ADC is configured to initiate start of conversion at every step time. And the encoder, as I mentioned earlier, is a 2048 line A quad B encoder. So Workbench allows you to bore down into a little bit more detail and change these settings even further. And the options available are dynamically updated based on what the user selects. For instance, if I change the ADC trigger from software to PWM trigger, it then provides the option of at which point in the PWM triangular waveform does the ADC start of conversion trigger needs to be happening. So similarly, all the other properties have multiple levels of settings that become visible based on the settings that the user chooses. As seen in the webcam view, the DC motor is connected to inverter 1 A phase and the inverter 1 B phase, and similarly the DC generator, which emulates the load torque, is connected to inverter 2 A phase and inverter 2 B phase. And the speed measured by the coupled DC motor generator set is fed back into A quad B encoder channel 1. And similarly, the inverter 1 A phase current is measured to do the inner current control for the DC motor, and the inverter 2 A phase current is measured to do the torque control for the load generator. So let's go back to our slides and continue from where we left off. And here are the results again that we just saw right now. So at this point, I would recommend that you pause the video and take a quick break, probably a 5 to 10 minutes break before we proceed to the next part of the session, where we'll look at AC motors and we'll look at the DQ control so that we can extend whatever we did for DC motor control for AC motor as well. And at the end of the next 1 hour, we will do the same thing where we will simulate an induction motor vector control and run it in real time as well, and do the same for permanent magnet synchronous motor as well. So at this point, you can all pause if you want a break and probably come back in 10 to 15 minutes. In the next 1 hour of the session, we should look at extending the concepts of DC motor speed control and applying them to induction motor and permanent magnet synchronous motor speed control. One of the major shortcomings of a DC motor drive is the requirement for commutator brushes. These carbon brushes lead to sparking and wear down as they slide against the copper slip rings. In addition, they also cause notches in the torque response. To avoid the use of slip rings and commutator brushes, in an AC motor, the windings are placed on the stator core. This leads to the issue that as the rotor rotates, and along with it the rotor-induced flux, the flux produced by the stator windings do not flip in direction, leading to an average of zero electromagnetic torque. To overcome this issue, in an AC motor, the stator consists of multi-phase windings which are spatially distributed. As seen in the slide, for the case of a three-phase system, the A-phase winding, B-phase winding, and the C-phase winding are spatially separated by an angle of 120 degrees. In addition, the density of each of the three-phase winding is sinusoidally distributed. This ensures that a balanced three-phase sinusoidal current induces a spatially distributed flux with a constant magnitude that rotates in time with a frequency that is determined by the frequency of the input current as well as the number of motor pole pairs. The image on the right shows the winding distribution for a single phase, namely the A phase. The winding distribution density as a function of angle theta is given by equation 1. Consider the stator slot at 90 degrees. Let's assume that the slot has 10 turns, which means that a slot that is at an angle 30 degrees away from it would have approximately 10 times sine of 60 number of turns in that particular slot. So that comes out to approximately 9 turns in the slot that is at an angle 30 degrees away. And another 30 degrees away, the number of turns at slot 6 would be equal to 10 times sine of 60, and that would be equal to half the number of turns, so 5 turns in that slot, and so on and so forth up until we reach 90 degrees from the initial angle, at which point the number of turns in that slot would be equal to 0. So what this essentially means is starting from the slot 1. Let's say there is one single turn that goes in and comes out, and at an angle of 30 degrees, the second slot is going to have 5 turns that goes in and comes out, and so on and so forth. And at an angle of another 30 degrees away, this slot is going to have approximately 9 turns that goes in and comes out. And at an angle of 90 degrees, it's going to have 10 number of turns that goes in and comes out. This is not exactly how a practical induction motor would be wound, but it's a good approximation for a theoretical consideration. The magnetic flux established in the air gap as a function of the angle is given by equation 2, where Lg is the air gap length, Ia is the magnitude of the current, and Ns is the total number of turns, and P is the number of poles. The magnetic flux is going to vary sinusoidally as a function of theta. The magnetic flux for A phase is going to be maximum when theta equal to 0, since the number of turns at 90 degree is the highest, and the flux induced by this turn is going to be perpendicular to the plane of the winding. Equation 3 represents the MMF in the air gap due to the flux induced by the current passing through the stator A phase winding. And the final equation is the magnetic flux density in the air gap due to the flux established by the current in the A phase winding. And when the air gap does not consist of any other material, as would be the case in most motors, the magnetic flux density is equal to the permeability of free space times the magnetic flux. So before we can model this motor in Workbench, we need to find out the equivalent electrical circuit as we did in the case of a DC motor. And the parameters that are needed to be known to model the system are the motor inductance, motor resistance, and the mechanical parameters. The self-inductance of any phase winding is given by the flux linking that winding divided by the current in the winding. And this consists of two components, which is the leakage component and the magnetizing component. The inductance due to the magnetizing component is a function of various motor dimensions and the number of turns in the particular phase. And the derivation for this is provided in the textbook that Professor Mohan had mentioned earlier. In addition to the self-inductance, there is also the mutual inductance, that is the flux linkage in other phase windings due to the current in any other phase windings. In this particular case, let's look at the mutual inductance due to the flux linkage in phase B winding due to the current in A phase winding. Let's initially assume that the B phase winding is aligned along the direction of the A phase winding. In this case, the flux linkage in the B phase winding due to the current IA would be the same as the flux linkage in the A phase winding due to the current in the A phase winding. Now let's assume the case where the B phase winding is at an angle 180 degree away from the A phase winding. In this case, the flux linkage in the B phase winding is going to be equal to the negative of the flux linkage in the A phase winding, both of it due to the current in the A phase winding. Now for any other case, it's going to vary as a function of cos of the angle between the A and the B phase winding. So in the case of a three-phase system where the B phase winding is at an angle of 120 degree apart from the A phase winding, the flux linkage component due to the current in the A phase winding into the B phase winding would be equal to cos of 120 degrees times the flux linkage in the A phase winding due to the current in the A phase winding. This is because only the cos component of the A phase winding links into the B phase winding, and the sine component is 90 degree and does not link the B phase winding. Thus, the mutual inductance between the A and the B phase winding is negative half of the per phase magnetizing inductance. Thus, the net magnetizing inductance of any particular phase winding equals to 3/2 times the per phase magnetizing inductance of that winding. Similar to the stator windings, the rotor windings also have their own magnetizing inductance as well as the leakage inductance. So far, we have considered the case where the flux due to a current in a stator winding links other stator windings. But there is also the scenario where the flux in the stator A phase winding due to the current in the stator A phase winding links to the rotor A, B, and C phase windings. In the case of stator to stator winding linkage, the windings were fixed and not rotating, thus the angle of separation between the two phase windings was always a constant. But in case of interaction between the stator and the rotor windings, the angle is continuously changing as the rotor rotates, and thus the coupling between the two windings changes as a function of the angle between the two windings. So having established the inductances of the motor, the only other component that remains is the rotor resistances. And these, unlike the inductances, are not a function of the rotor position or the winding distribution. Thus, using these parameters, a system of equation can be set up where, given 3 stator voltages and 3 rotor voltages and a load torque, the 3 stator currents and the 3 rotor currents and the motor speed can be computed. But this involves extensive computation as there are 6 sets of equations that needs to be solved. This can be further simplified by relying on the fact that in any balanced 3-phase system, the sum of the 3 phase quantities would always be equal to 0. So consider 3 independent variables. Let it be either 3 voltages, VA, VB, VC, or IA, IB, IC. And these 3 variables occupy the complete 3D space as shown here. But as I mentioned earlier, in a balanced system, sum of 3 phase quantities would always be equal to 0. Thus, this reduces the vector space to just a single 2D plane as shown on the right. And this means that the 3 independent variables can be reduced to 2 dependent variables, and we can use space vectors to convert these 3 dependent variables to 2 independent variables by using a simple rotational transformation. So the space vector equations are presented in the slide. This is merely a rotational transformation expressed in Euler form to keep it concise. So in case of a 2D rotational transformation, it would involve cos theta, sin theta, and negative sin theta, and cos theta. So we would multiply xy vector by this matrix to transform it to a rotated vector in a different plane, alpha beta. So the same can be extended to 3 variables, which is represented by this equation on the top. And all the motor variables such as voltage, current, flux, all of these can be transformed into space vector merely on a mathematical basis since all of these are in a balanced system, and thus they can all be reduced from 3 dependent variables to 2 independent variables. In this slide, the flux linkage that was derived in the previous slide is rewritten in space vector form as shown here. And similarly, the rotor flux linkage space vector can also be rewritten in this form. It must be noted that the stator flux linkage space vector was written with respect to the stator A phase magnetic axis, and the rotor flux linkage space vector was written with respect to the rotor A phase magnetic axis. When we look at the stator A phase flux linkage, due to the contributions from the stator current as well as the rotor currents, it is equal to the self-inductance times the stator current plus the magnetizing inductance times the rotor current. In this equation, all the parameters are with respect to the stator A phase magnetic axis. The rotor current with respect to the stator A phase magnetic axis can be obtained by projecting the rotor current with respect to the rotor A phase magnetic axis onto the stator A phase magnetic axis. And the angle between the stator and the rotor magnetic axis is equal to the angle of rotation, which is theta m. Resubstituting equation 2 back into equation 1, we obtain the stator flux linkage equation, which consists of the flux linkage contribution due to the stator currents as well as flux linkage contribution due to the rotor currents. And the stator space vector voltage equation is given by the drop across the stator resistance plus the change in the stator flux linkages. One of the issues in modeling the system and designing a controller for it is the presence of e power j theta component in our equations. This would prevent us from expressing our system in transfer function form, thus complicating any controller design. To avoid this j theta component, instead of projecting our space vector onto a fixed axis, we can project our space vectors onto a rotational reference frame. This is what we are going to achieve by use of DQ windings, as shown in this image here. By use of space vectors, we have already reduced 3-phase winding system into a 2-phase winding system. Now, instead of having those 2-phase windings on a fixed axis, let's consider that the axis of winding itself can be rotating. There are different options for the speed of this rotational frame, and most common choices are a fixed rotational frame, a synchronously rotating frame, and a frame that rotates with respect to the motor speed. Each of these options have their advantages, and based on the design requirements, one of these 3 options would be chosen. For our particular session, when we look at vector control, we would look at the case where this DQ frame rotates at synchronous speed. This allows all of the space vector quantities to be projected onto a rotating frame, which would lead these quantities to become DC component instead of sinusoidally varying components. When we convert the 3-phase windings into 2-phase equivalent windings, we scale the per phase magnetizing inductance by a factor of 3/2. This ensures that the power calculated by the inner product of the DQ voltages and the currents would be same as the power calculated in the time domain for the 3-phase windings. That is, this choice leads to power invariance between the transformation. Other textbooks and papers would use different factors that leads to different properties of the DQ windings. In this slide, the current space vector is projected onto the rotating DQ frame as given by equation 4 and equation 5. Similarly, the rotor windings can also be represented by 2 DQ windings in the rotational reference frame. In this rotational reference frame, the flux linkage equations do not contain the e power j theta component that we saw in the stationary reference frame earlier. The flux linkage equation in this modified DQ reference frame is given in the slide. Let's consider the case of the stator d-axis flux linkage. Only the windings along the d-axis contribute to any flux linkage in the d-axis windings, and the currents in the q-axis winding do not contribute to any flux linkage in the d-axis winding. Thus, the flux linkage in the stator d-axis winding is equal to the self-inductance times the current in the d-axis stator winding plus the magnetizing inductance times the current in the rotor d-axis winding. And similarly, expressions for the flux linkage of all other 4 windings can be written. To transform a system from ABC to DQ coordinates is simply to transform the system from ABC domain to alpha beta space vector domain and then transforming it into a rotational coordinate, which is in the DQ frame. So when we converted from ABC to alpha beta domain, which was again stationary reference frame, we used the transformation matrix E par theta, E par 0, E par j2 pi by 3, and E par j4 pi by 3, which is same as the commonly used rotational matrix cos theta sin theta minus sin theta cos theta, which was for a 2D frame. We are extending it to a 3D frame. And to convert it from alpha beta to DQ, we just have to use a rotational transformation, which is from two-phase to two-phase. So which is the common rotational transformation that's well known, cos theta sin theta and sin theta cos theta. So when we multiply this 2 cross 2 matrix, which is cos theta sin theta and minus sin theta cos theta, along with our previous ABC to alpha beta transformation or ABC to space vector transformation matrix, which is a 2 cross 3 matrix, we end up with this new 2 cross 3 matrix, which is the function of the rotational angle of the reference frame as well. All phase quantities can be transformed from ABC to DQ. And the inverse matrix to calculate ABC to DQ is also shown here. The inverse can be obtained by simply extending this matrix and adding one more equation, which is the dependent equation, is equal to 0. So this becomes a 3 cross 3 matrix, the inverse of which can be found, and that would be this particular matrix shown here. Now that we can convert ABC quantities into DQ quantities, let's go ahead and write out the equation for the stator voltages in the DQ frame. This is the equation from a previous slide where the stator voltages are represented in space vector or in the alpha beta frame. This can be transformed to the DQ frame by acknowledging the fact that from DQ to alpha beta is merely a rotational transformation. This equation in the previous slide can be written in matrix form. Substituting these alpha beta quantities with their DQ equivalent results in this particular equation where Vs alpha beta is equal to Vs dq times E par j theta, and similarly Is alpha beta is equal to Is dq times E par j theta. E par j theta terms get cancelled out, and similarly lambda S alpha beta is equal to lambda S dq times E par j theta, but we have a differential term, so we get d by dt of lambda times E par j theta. Again, E par j theta terms gets cancelled out, and then we have lambda times d by dt of E par j theta, which yields omega t times E par j theta, j omega d times E par j theta. So this is our Vs dq equation, and if you look at this equation, this is very similar to what we had for a DC motor, where we had Va is equal to Ra times Ia plus we had d by dt lambda A, and in that case d by dt lambda A is same as La times di by dt, because that is equal to L into I, and L was not varying. But in this particular case, because of the rotational nature of the windings, we have an inductance that varies as well. And hence we have d by dt of lambda component as well as a lambda that is a function of the speed at which a frame of reference is rotating. And similarly, we can derive the equation for the rotor voltages as well, as a function of the rotor current and the rotor flux linkage. So we can rearrange this voltage equation to solve for the flux linkage as shown in the slide. So the d lambda by dt is equal to the stator voltage minus the drop across the stator resistance minus the drop due to the cross coupling of the flux linkages. Similarly, the same equation can be rewritten for the rotor flux linkage as well. And the model to implement this is shown on the right here. So we have the stator voltage minus the drop due to the stator resistance minus the drop due to the cross coupling of the flux linkages, which would equal to d by dt of the flux linkage. And once we integrate it, we will get the flux linkage, which we again loop it to solve for the flux linkage equation. Once we have the flux linkage, we can directly obtain the d and q axis currents based on the formula that we saw a couple of slides back. And this equation is rewritten in matrix form in the slide, where lambda SD, which is the flux linkage in the d-axis, is equal to the self-inductance of the d-axis times the d-axis, stator d-axis current, plus the magnetizing inductance times the rotor d-axis current. And similarly, we can write out the equation for the rotor d-axis flux linkage as well. And similarly, the stator q-axis flux linkage and the rotor q-axis flux linkage. And it can be represented in a compact form as a 4x4 matrix, which linkages all the stator and the rotor currents, D and Q, with the stator and the rotor flux linkages, both D and Q axis. So with that, we have implemented the electrical part of the motor model. We have established the equations necessary to go from motor terminal voltages to the motor terminal currents. The one last remaining component is the mechanical model, which requires the knowledge of the electromagnetic torque that is generated. Now, the derivation for this formula is presented in the textbook, but to get an intuitive feel of what this means, the torque produced by the d-axis winding due to the current in the d-axis winding is going to be proportional to the current in the d-axis winding times the flux linkage in the q-axis winding. The current in the d-axis winding is going to produce a flux which is orthonormal to the plane of the winding, and this flux linkage is going to interact with the flux produced by the current in the q-axis winding. And these two interactions are going to produce a torque along the d-axis. And another component in the torque is the number of pole pairs. The image shown here is the electrical equivalent circuit. The same winding distributed mechanically would be a function of the number of pole pairs. So if we had 2 pole pairs, then the number of dq equivalent windings is going to be 2. This d-axis is going to produce a torque due to the flux linkage in the q-axis and the current in the d-axis, as well as this d-axis is going to produce a torque due to the flux linkage in its corresponding q-axis and the current in its d-axis. So these two axes are going to produce a combined torque, and hence the factor P by 2 is introduced into the equation. And similarly, we can determine the torque in the q-axis winding because of the current in the q-axis interacting with the flux linkage in the d-axis. With this, we know all the equations necessary to model the motor in the DQ frame. So we have the applied terminal voltage, which is the stator voltage, and we have the rotor voltage, which in case of a squirrel cage induction motor, which we will be considering during this session, would be 0, since the rotor is just an iron cage with copper rings that are shorted in the end. And if it were going to be an induction, doubly fed induction generator, there could be non-zero terminal voltages as well. And in case of permanent magnet synchronous motor, this is going to be a permanent magnet, so this component would not exist at all. There is just going to be a flux along one of the axes, and there is going to be no rotor voltage component. So we have the voltage, and then we subtract the rotor resistance, the drop due to the rotor resistance, and we subtract the drop due to the cross coupling of the flux linkages, and we integrate this to obtain the flux linkage. And we multiply the flux linkage by the inverse of the inductance matrix that we saw earlier, and we will get the DQ currents. And from the DQ currents from the previous slide, we can obtain the electromagnetic torque. And after this, this component is same as what we would have in a DC motor, or for the matter any motor. So you have the electromagnetic torque minus the load torque, and you integrate the differential torque across the rotor shaft, you end up with the motor mechanical speed. And we scale the motor mechanical speed by the pole pair to convert it into equivalent electrical speed. So here is the overall system modeled using Workbench. Let's go ahead and open this model and look at it in a little bit more detail. So as I mentioned earlier, anybody who's interested can follow along using the link that's provided in the slide. And right now we are going to be doing part 4 of our example. So we have the stator flux linkage equation that I showed before. So we have the stator voltage minus the drop due to the stator resistance minus the drop due to the cross coupling of the flux linkages. The output of this sum would be the differential of the stator flux linkage in the DQ frame. And when we integrate it, we get the stator flux linkages lambda as DQ. And we do the same thing for the rotor as well. The equations are exactly the same. The only difference being that the stator voltages are going to be 0 because we are going to simulate it for a squirrel cage induction motor, which I mentioned earlier is just an iron cage with shorted end copper rings. And in the stator, we have a three-phase voltage that is being applied with a magnitude VA and at a frequency F. And these parameters are defined in the init file here. So we are applying a voltage of 460 volts, line-to-line RMS, and we are applying a frequency of 60 Hertz. As I mentioned earlier, the DQ frame could be rotating in any speed, but for our session, since we are more interested in the vector control aspect of it, our DQ frame is always going to be rotating at synchronous speed. This ensures that our DQ frame is rotating at the same speed as all our space vectors. That means when we project these space vectors onto the DQ windings, we are going to end up with DC quantities rather than AC quantities. And the advantage of having DC quantities instead of AC quantities is we can extend all the controller design that we used for the DC motor earlier and apply them to the controller design of AC motors as well. So once we get the DQ flux linkages, we multiply it by the inverse of the inductance matrix, which is derived here. So this is the inductance matrix M. And we multiply by the inverse of it to get the IDIQ currents. And once we have the IDIQ components, we can get the torque from the equation that was shown in the slide earlier. And from the torque, we can obtain the differential torque by subtracting out the load torque. By integrating it by 1 by Js, we'll end up with the motor speed, the mechanical speed, which we then again scale by the pole pair to obtain the electrical speed. In this example, we have assumed that the motor is already in steady state. We are not going to start the motor from zero initial condition. We are already assuming that the motor is in steady state, and we are going to simulate a condition where we apply a change in the load torque. So initially the motor is running in steady state at rated voltage and rated frequency and rated load condition. And at 0.1 second, we are going to reduce the load torque by half and see how the motor speed changes once we change the load torque. So all of the integrators in this model are pre-initialized to an initial condition, which is the rated load condition and the rated voltage condition. And these initialization values are computed in the init file that's shown here. As I mentioned again, the step-by-step procedure to do this is given in the link that's provided in the slides. So let's go ahead and simulate the system. The solver that we are using is a Runge-Kutta solver, and we are using a step time of 1e minus 5 for this particular simulation. So let's go ahead and look at the results. As you can see, initially the motor is operating under steady state condition with rated load torque, and at 0.1 second, we are cutting the load torque by half. And as you can see, the electromagnetic torque matches the load torque in steady state. Similar to our DC motor simulation, we are assuming that the viscous frictional component is zero since it's only a simulation. So the electromagnetic torque is always going to converge to the load torque at steady state, but there's going to be some bit of oscillation before it goes and settles down. Now, if you look at the speed, it is going to operate at the rated speed in steady state condition for rated load. And once we reduce the load by half, it is expected that the motor is going to accelerate and settle down at a new operating speed, which is higher than the speed when it was operating under rated load condition. Similar to our DC motor, the induction motor has the same issue when operated under open loop condition. That is, the speed varies as a function of the applied terminal voltage and frequency, as well as the load torque. So in order to control the speed of the induction motor, we need to use some form of closed loop control. So let's go back to our slides and look at extending the concepts that we had derived for DC motor closed loop speed control and apply them to the induction motor speed control as well. And once again, here are the results that are obtained from simulating the system. In the traditional implementation of vector control of an induction motor, we align the d-axis of the DQ frame along the rotor flux linkage space vector. What this means is there is going to be no rotor flux linkage along the Q axis. Thus, lambda RQ is going to be 0. And again, the differential component of it is also going to be 0. This significantly reduces the cross coupling between the D and Q axis and simplifies the equations further. So with these assumptions, the equations that we had seen in the previous slides are rewritten in equations 1 through 6. The model on the right shows how to obtain the rotor flux linkage space vector position from the measured stator currents and the motor speed. It is evident from this reduced torque equation based on the assumption that lambda RQ is 0 that the generated electromagnetic torque is purely a function of the stator Q axis current. And similarly, the rotor flux linkage, which is in turn equal to the air gap flux linkage, is solely a function of D axis current alone. Here is the overall induction motor vector control model. As mentioned earlier, you can control the rotor flux by directly controlling the stator D axis current. And we can control the electromagnetic torque by directly controlling the stator Q axis current based on the two equations that we saw in the previous slide. Similar to our DC motor speed control, we can cascade a speed PI controller and further extend it by cascading a position loops PI controller as well to the system. In most operations, the rotor flux linkage lambda RD is usually maintained at the rate of rotor flux linkage. This ensures a fast dynamic response. And in cases where the DC bus voltage is limited and a higher speed is desired, this field can be weakened so that we can obtain a much higher operating speed at the cost of reduced maximum torque. The design of the speed PI controller is similar to the design for DC motor drive. We have the KPKI, which is the PI controller, and we have the mechanical transfer function, which is 1 by SJ, and we have a KT, which is the torque constant, which converts ISQ to electromagnetic torque. And that is given by this formula, which we had seen in the previous slide, which was obtained by the simplifying assumption that in vector control, we are going to align our DQ frame with respect to the rotor flux linkage space vector. And this whole thing can be assumed to be a constant because ISD is maintained a constant, or in the cases where ISD varies due to field weakening, it varies at a rate much, much slower than the speed at which the electromagnetic torque changes. So to design the inner current control loop, we need to write down the voltage equations. Substituting the reduced equations obtained in slide 73 into the voltage equations in slide 63, we obtain the following two stator voltage equations, where sigma is the leakage factor, which is given by 1 minus Lm squared by Ls Lr, and it's very close to 0 when the leakage component is much, much lower than the magnetizing component. This equation is very similar to the voltage equation for a DC motor, where we had VA is equal to RA times IA plus LA times DI by DT. These two equations are very similar, with RS being equal to RA and LA being equal to sigma times LS. The other two components can be ignored for our controller design because of the fact that lambda RD is going to be maintained a constant, and the second component is almost equal to 0 because sigma is very close to 0. And similarly, in the VSQ equation, we can ignore these two components because the fact that lambda RD again is going to be a constant, so it does not affect the controller design. It can just be ignored as a constant disturbance, and this component is going to be very close to 0. So from the previous slide, the voltage equation for the controller design can be written as this, where we have ignored the cross-coupling terms as disturbances. And this equation can be written in transfer function form as shown here. And if you go back and look at the slides for the current controller design for the DC motor drive, this transfer function is very similar to the transfer function we had for the DC motor as well, which was RA, 1 by RA plus S times LA. So the PI controller design for the inner current control loop for an induction motor in DQ frame under vector control would be the same as the current controller design for a DC motor drive. So let's go ahead and implement this full model with the PA controllers for speed control of an induction motor in Workbench. So as I mentioned earlier, anybody who's interested can follow along using the link that was given in the slide. We are going to be doing part 5 of our example, and which is the induction motor vector control. So we have the motor model that we are just using from our previous simulation that we had designed. And I've just placed them all into a subsystem. And we are going to measure the current and the speed. And based on the current and the speed, we are going to obtain the rotor flux linkage space vector position based on the model that was given in slide 73. So we have the measured current, ISD, ISQ, and the speed. And from that, we can compute the rotor flux linkage space vector position. This position is necessary because we need to align our DQ frame with respect to the rotor flux linkage space vector for vector control. We implement that equation that was shown in the slide, and we obtain the stator flux linkage space vector position theta. We use this theta wherever we are converting DQ quantities to ABC or ABC quantities to DQ frame. So for the D-axis current, so we can control two components now, the D-axis current as well as the Q-axis current. In a DC motor, we could only control one component because there was only one control variable, which was the applied terminal voltage. But in AC motors, you have two control variables, namely the magnitude of the applied terminal voltage as well as the frequency of the applied terminal voltage. In a balanced system, you can't adjust the phase shift of the applied terminal voltage. It's always going to be phase shifted by 120 degrees. So you essentially have just two control variables. And by using DQ transform, by using alpha beta transform as well as a DQ transform, we have converted those two control variables into two control VD and VQ voltages as the control variables. So which in turn allows us to control the ID current as well as the IQ current. And as I mentioned earlier, ID current, the stator ID current controls the flux linkage in the air gap, and the stator IQ current controls the electromagnetic torque that's generated by the motor. The loop that controls the electromagnetic torque can be further extended by an additional PA controller to do speed control. And inside this, we just have simple P and I controller, same as what we use for a DC motor. And we have the integral controller with an anti-winder, and the output of which is summed up and limited by a saturation block because of the practical limitation of the inverter that we are going to be using. The current limit for the inverter that we're using is 5 amperes. So I've set the upper and lower limit for the integral anti-wind-up as well as the saturation block at 5 ampere. And similarly, the voltage is going to be limited based on the modulation algorithm that we are going to be using. And since we're using a sine PWM, the maximum voltage that we can get given the DC bus voltage is about 20 volts. So all the motor parameters are initialized in the initialization file, IMParam, where all the values are computed, and the PA controller values are computed in the init file as well as given here. So this is solved by solving the two equations that we had seen earlier. That is, the phase margin must be equal to some desired value, and the crossover frequency must be also equal to some desired value. So for this particular example, we are using a phase margin of 60 degrees, and we are using a crossover frequency of 125 radians per second for the speed loop. And for the current loop, we are using 10 times that, which puts it as 1250 radians per second. So we are starting the motor with zero initial condition, that is zero applied voltage, zero current, zero speed, and zero torque. We are stepping the reference speed from 0 to 100 radians per second at time equal to 2 seconds. And after 4 seconds, we are applying a small load torque of 0.05 Newton meter. This is an extremely small induction motor, and hence the reason we are using a very small load. Once again, we are using a Euler solver, and we're using a step time of phi e minus phi. So the choice of the step time is going to be determined by the time constant of the various transfer functions that we are used in this model. So we have the mechanical transfer function, which is 1 by Sj plus b, the time constant of which is going to be very, very high, so we don't have to worry about it. And then we have the time constant of the electrical system, which is 1 by SL plus R. And then we have the bandwidth of the control loops. So we want to set the step time so that we have at least 10 to 100 samples within a time period that is equal to the smaller time constant of the system. And in this particular case, 5e minus 5 more than satisfies that. So let's go ahead and run the system and look at the results. Let's start off with the motor speed. 2 seconds, we step the reference from 0 to 100 radians per second. And as you can see, the PI controller compensates for the difference in the reference and the actual speed and ensures that the actual speed settles down at the desired reference speed. And if you look at 4 seconds, we apply the additional load torque, and thus the speed drops a little bit, but the PI controller recovers it quickly, and the speed again settles back down to 100 radians per second. Let's go ahead and look at the IDIQ currents. So as I mentioned earlier, we want to maintain the ID current at the rated conditions so that we have fast dynamic response. And as you can see, the ID current is always a constant at about 1.2 amperes. And if you look at the IQ current, it starts off at 0 because initially there is no need for torque because there is no load torque and there is no applied voltage, and the motor is not accelerating. So there is no electromagnetic torque being generated. So IQ current is going to be 0. Once the motor starts accelerating, we see that there is a need for IQ current because the electromagnetic torque is proportional to the IQ current. And thus you can see the IQ current increases. And the IQ current is limited to about 5 ampere because that's the limit we set in the saturation block of the PI controller. That's because our inverters are rated for a little over 5 amperes, so we don't want to exceed that particular value. And once the motor settles down at 100 radians per second, the IQ current drops to almost 0, and there is only a residual current because we have a frictional component modeled as well in our motor model. So if you go to our motor model, in addition to inertia J, we also have a frictional component B as well, so 1 by Sj plus B. So there is going to be a residual current to sustain the frictional torque that is needed, the viscous friction due to air. And once we load the motor with a load torque at 4 seconds, you see the IQ current increase proportionally to compensate for the increased load demand. And once the IQ current settles, the load torque would be equal to the electromagnetic torque, and thus the speed would settle back again to the reference speed at steady state. So that concludes the simulation part of the induction motor vector control. Let's go back to our slides and look at the real-time implementation of induction motor vector control next. So this is again the initialization file that I showed you in the simulation model, and these are again the results. So to implement the induction motor model in real time, we'll be using the actual hardware. Once again, as I mentioned earlier, if you already have the hardware acquired, you can follow along using the link that's provided in the slide. And if you don't have the hardware, you can obtain it from the Sciamble website. In the cusp lab kit, you can have the electric drives lab kit here, which has all the 4 motors, 2 DC motor, PMSM motor, and an induction motor, as well as the inverter module, which has the onboard controller in it that is necessary to run this particular experiment. So let's go ahead and open the model in Workbench. This is going to be part 6 of the ECCE videos that is available on the website. When we did our DC motor speed control, we used 2 different models for simulation as well as for real time, just to keep things simple. But as I mentioned to you earlier, we could have used the same model for both simulation and real time. So that we'll demonstrate in this example, where we're using the same model for both simulation as well as in real time. So this part of the model is exactly the same as what we did in part 5, where we simulated an induction motor vector control. We have an induction motor model in the DQ frame, and we have the PA controller, the inner current controllers for ID and IQ, stator ID and IQ, and we have the outer speed loop controller. And on the top here, we have the estimator model, which takes the measured ABC currents and the motor speed and determines where the rotor flux linkage space vector is, so that we can use that in the ABC to DQ as well as DQ to ABC transformations. In addition to the induction motor, on the bottom we have a DC motor because this is a coupled motor generator combination. In our simulation, we use just a step toolbox to simulate a load condition, but in real time we need to have another motor coupled that can emulate a load. So we have a DC motor that is being run in torque control, or since in a DC motor the torque is proportional to the armature current, we are running this in current control, and we are applying a load step in the current, which in turn translates to a load step in the torque. the difference between the electromagnetic torque and the load torque, the differential torque is integrated and divided by 1 by J, which is the moment of inertia. And this integration is going to give you the motor speed. We use this motor speed in our PA controller as well as in our estimator model. So let's go ahead and run this in simulation mode. If we look at the results, it's going to be exactly the same as what we obtained when we had in our previous example. So the only difference between that and this is we are using a DC motor to simulate a load rather than using a step function to simulate the load. Three-phase currents are shown here, the stator ABC currents. And we can look at the same thing and once we have transformed it into the DQ domain as well. So as you can see, the results are exactly the same. In this particular simulation model, we haven't used 1 by Sj plus B, we have just used 1 by Sj. And hence you don't see a residual component in the current once the speed settles down at the desired speed and the rated and the load torque is 0. And the IQ current also goes to 0. To convert this simulation model into real time, all you have to do is add additional tools that can allow us to measure the currents and the speed. And these tools are available in the hardware integration toolbox that's part of the tool sets that provided pre-built in Workbench. So we drag and drop the ADC toolboxes here to measure the IA current and the IC current, and IB current can be obtained by acknowledging the fact that the sum of the three currents equal to 0. So IB equal to negative IA minus IC. So we have the IA, IB, IC currents measured here. So the output voltage, whatever we obtain from the PA controllers, in simulation we directly connect it to the motor. But when we want to do it in hardware mode, we convert them to duty cycles and connect it to the PWM blocks. And we do the same thing for the DC motor as well. We connect the output voltage to the PWM blocks. And again, for the DC motor, we use an ADC to measure the current of the DC motor. Finally, in simulation, the output of this integral would have been the speed. When we have to do it in real time, we need an AQB block, which measures the speed. So if you look at the properties, there is a brief description that you can see here that explains what the AQB block does. So this measures the speed. And in simulation mode, this would not affect what the output of the integral is. Whatever the output is going to be bypassed and fed back to the PA controller's feedback. But in real time, it is going to ignore whatever the integral output is going to be and rather measure the signal from the actual encoder and provide it to the controller. So once we click the hardware mode, as you can see, the software intelligently identifies that the induction motor and the DC motor model need not be programmed in real time, and it grays it out so that it is not converted into real-time C code. And only the controller function, the estimator model, and the measurements are coded in real time. Data is logged back to the computer through the USB port. So let's go ahead and run this model in real time and look at the results. Here's the setup that we are going to be using for this example. It is very similar to the one that we use for the DC motor speed control. It has the same inverter module and the DC generator to generate the load torque. The only thing that has changed is instead of using a DC motor, we are going to be using an induction motor. So the motor on the right is a three-phase induction motor that has a rating of 24 volts line-to-line RMS and a rated frequency of 60 Hz and rated current of 2.8 ampere peak. The induction motor is going to be under speed control, and the coupled DC generator is going to emulate a load torque. So let's go ahead and run this example. And as before, the speed and the current signal measured by the microcontroller is logged back to the computer via the USB. And some of the scopes have been disabled to increase the resolution of the data that is logged. So here is the response of the speed logged in real time. As you can see, at time equal to 1 second, we applied a step in the reference speed, and the PA controller compensates for the difference and brings the measured speed equal to the reference speed at steady state. At time equal to 3 seconds, we applied a small load torque using the coupled DC generator, and as can be seen, the speed dips momentarily before the PA controller compensates for the error. So let's look at the ID/IQ currents. The IQ current maintains the rotor flux linkage at rated 1.2 ampere, and the IQ current is 0 until the motor starts to accelerate at time equal to 1 second when the reference speed changed. And once the motor reaches steady state speed, the IQ current dies down to just the residual component necessary to sustain the torque component due to viscous friction. And at time equal to 3 seconds, we apply a step in the load torque, and thus the IQ current proportionally increases to compensate for the load torque in addition to the viscous friction as well. Let's look at the induction motor torque versus the coupled DC generated load torque. The graph in the red is the induction motor electromagnetic torque, and the graph in the green is the load torque that is emulated by the coupled DC generator. Between time period 1 and 3 seconds, the generated load torque is set to 0, while the electromagnetic torque of the induction motor has a residual value, as mentioned earlier, to compensate for the viscous torque. And at time equal to 3 seconds, the generator's torque is stepped to about 0.08 Newton meter, and similarly, in the induction motor, electromagnetic torque also steps by the same value. One of the interesting features in Workbench is the ability to compare the results that have been obtained in simulation with that of the results obtained in hardware. So let's stop this hardware mode and let's rerun this in simulation mode and look at the speed results. So we can swap back and forth between the results that we obtained in the simulation mode and the results that we obtained in hardware mode and make comparative analysis of the differences between them. So as can be seen here, the speed in the simulation matches very closely with the speed that is obtained in real-time mode. This is because the parameters that we have estimated for the motor is very close to the actual parameters. If the parameters were significantly off, then the response would not match between the simulation and the hardware. Finally, let's look at the current scope, the IDIQ current. So as you can see in simulation, the D-axis current is a constant 1.2 ampere and the Q-axis current is 0 until a load torque is applied. But if you look at the hardware mode, the Q-axis component has a residual current even before the load torque is applied because it needs to compensate for the viscous friction. But in our simulation mode, we just use 1 by Sj and we didn't use the transfer function 1 by Sj plus b, so we ignore the viscous friction in simulation, and hence the difference between the results obtained in simulation versus that obtained in real-time hardware. And similarly, the torque result obtained in simulation, the electromagnetic torque matches exactly with the load torque under steady state in simulation, but in reality there's going to be a discrepancy because of the viscous friction component. In our simulation, if you had modeled the viscous friction component as well, we could have had similar performance in simulation for the mechanical system as well. So let's go back to the slides and continue from where we left off. So that concludes the induction motor vector control in real time. Let's look at running this in permanent magnet synchronous motor as well. So these are the results again. The three-phase currents, just zoomed in a little bit, the IDIQ currents, and the induction motor torque and the load torque. The DQ concept that we derived for induction motor can be easily extended for a permanent magnet synchronous motor, and it's much more simpler for a permanent magnet synchronous motor because of the fact that the rotor is a permanent magnet and it does not have any windings. In this session, we are going to consider the mathematics of only a non-salient pole permanent magnet synchronous motor, which has the magnet attached on the surface of the rotor core. This leads to the inductance along the D-axis as well as the Q-axis to be the same. The other variant of this is a salient pole permanent magnet synchronous motor, which has slots bored into the rotor core into which the magnets are inserted. In these motors, the D-axis inductance and the Q-axis inductance are different, and this has the advantage of increased torque production due to the reluctance torque as well, in addition to the magnetic torque. And it also allows precise sensorless vector control even when the motor parameter varies significantly by use of high frequency injection. We will not be looking at those in this tutorial session, but those concepts are explained in detail in the textbook that Professor Mohan had mentioned earlier. So in case of an induction motor, the stator D-axis flux linkage was equal to the stator inductance times the stator D-axis current plus the magnetizing inductance times the rotor D-axis current. And in case of the permanent non-salient pole permanent magnet, the stator component is going to remain, but the rotor component is going to be 0 because there is going to be no rotor current. And in vector control of a permanent magnet synchronous motor, similar to an induction motor, we are going to align the DQ frame along with the rotor flux linkage space vector. So there is, in addition to the flux linkage due to the stator current, there is also going to be a flux linkage due to the rotor permanent magnet, which is given by lambda FD. And since the DQ frame is aligned with the rotor flux linkage, this rotor flux linkage component is not going to be reflected along the Q axis. So the Q axis flux linkage is going to be just a function of the Q axis current alone. Apart from this, the rest of the equations are exactly the same as what you would have with an induction motor. The VSD, VSQ equations are the same. And you have the torque equation, which is reduced because there is going to be no component in the Q axis, flux linkage component in the Q axis. So the torque is just a function of interaction between the rotor flux, which is along the D axis, and the current in the Q axis of the stator winding. And the mechanical equations are going to be the same across AC motors as well as DC motors. There is no modifications in those equations. So here is the hardware. On the right, we have the permanent magnet synchronous motor. On the left, we have a DC generator to emulate a load. And we have the encoder, which measures the speed. And the inverter has all the current sensors necessary to measure the three-phase currents as well as the DC currents. And the inverter has an onboard microcontroller, which Professor Mohan will explain a little bit more in detail in the next 20 minutes. And this microcontroller takes in all the measured signal and generates the gate signal, which drives the inverter, power inverter modules that are present to generate the desired output voltage to drive the motor. Here is the workbench model to do a permanent magnet synchronous motor vector control in real time. Let's go ahead and open this example. As I mentioned earlier, again, this example can be followed along if you have the hardware module that is available on the Sciamble website, as well as you can go to the link that's shown in the slide and follow along the step-by-step procedure that's highlighted in the website. So for this example, again, I've just used the hardware model alone. There is no simulation model here, but in the example files that are available in the Workbench software, there is a simulation of induction motor vector control available as well. And just to keep things simple, I'm just going to be using a hardware model alone. Unlike an induction motor, where the rotor flux was induced by the currents in the stator winding, in a permanent magnet synchronous motor, there is a permanent magnet that establishes the rotor flux. Thus, the initial position of the rotor magnet needs to be known because our DQ frame is aligned with respect to the rotor flux linkage space vector. So in a permanent magnet synchronous motor, we initialize the position of the rotor by initially giving a step voltage in the A-phase winding alone, so that the rotor position shifts so that the rotor flux linkage space vector aligns with respect to the stator A-phase magnetic axis. So we run the rotor init model first in real time, which initializes the rotor position so that we know exactly where the rotor is before we start the vector control algorithm. So let's go ahead and run this model in real time to initialize the rotor position. Here's the view of the setup that we are going to be using for this example. All of it exactly the same as the setup that we used for the DC motor speed control as well as the induction motor vector control experiment, except for the motor on the right, which is a permanent magnet synchronous motor. The motor is rated for 7.1 ampere continuous and a rated speed of up to 6000 RPM. The power rating of this motor is almost thrice that of the induction motor that we saw earlier, and the size is almost half to 1/3 of the induction motor. In general, a permanent magnet of similar rating as that of an induction motor would be somewhere between 1/4 to 1/8 the size. So let's go ahead and run this system. Once we run this model, there is going to be a small rotation so that the rotor magnet aligns with the stator A-phase axis. And the degree of rotation is going to be determined by the number of pole pairs of the motor. This might not be always feasible in practical applications where uncontrolled rotation might not be allowed. In those scenarios, instead of using an incremental encoder, we would usually use an absolute encoder so that the initial position can be known even when the system is powered up after a complete power down. Alternatively, Hall effect sensors could be provided on the motor so that one of the three faces or combination of two, which is closest to the rotor pole, is excited instead of exciting the A phase by default. This would ensure a minimum possible initial rotation for alignment. Now that we have initialized the rotor position, let's go ahead and run the permanent magnet synchronous motor vector control algorithm. So let's close this and let's set the model run file to the vector control model. So let's go ahead and run this model. And same as before, the motor currents and the speed is logged by the controller back to Workbench through the USB. And here is the plot of the permanent magnet synchronous motor speed in real time being logged back. And same as before, at time equal to 1 second, we step the reference from 0 to 100 radians per second, and the PA controller ensures that the motor speed settles down at the desired reference speed. And at 3 seconds, we apply the load torque, and thus the motor speed dips a little bit, but recovers quickly and settles back at 100 radians per second. And if you look at the ISDQ currents, in case of the induction motor vector control, we had a ISD current component which was non-zero because the stator currents established the rotor currents, which in turn establishes the rotor flux linkage. But in case of permanent magnet synchronous motor, we have a permanent magnet on the rotor, and hence the stator does not need to establish any flux in the air gap. Thus the ISD current is going to be zero. In systems with limited bus voltages, in order to achieve higher speeds, the ID current can be maintained at non-zero value so that we get higher speeds at the cost of lower maximum torque. But in this case, we are maintaining the ISD current to be at zero. There is an increase in the ISQ current when the motor is accelerating because the reference change at time equal to 1 second, and once the motor speed reaches steady state at approximately 1.25 seconds, the ISQ current settles down to the residual current that is needed to maintain just the frictional losses. And at 3 seconds, as soon as there is a step in the load torque, the ISQ current increases to satisfy both the load torque as well as the torque due to the viscous friction. And as I mentioned earlier, you can try out all of these examples at your own convenience. And for those of you who are interested, there's a complete lab manual available for both the basic drives lab and as well as the advanced electric drives lab. With it, let's stop this model and go back to our slides. So that concludes the permanent magnet synchronous motor vector control experiment. Let's go back to our slides. And these are the results once again shown here. The stator three-phase currents and the zoomed in stator three-phase currents. And here's the stator DQ current. And you have the electromagnetic torque as well as the load torque. So the applications that we have seen here so far was very specific to motor drives, but Workbench can be used for many other applications as well. And one of the interesting applications that we are using in our labs right now is to use Workbench and its code generation feature to run a matrix converter hardware in real time. Here's the image of a 3-level neutral point clamp matrix converter that generates desired output voltage at desired magnitude and frequency directly from a 3-phase input voltage. This converter consists of 12 bidirectional switches, which are implemented using 24 discrete switches, where 2 switches are connected in common emitter configuration to generate a bidirectional switch. And this is the controller board that's used to drive the matrix converter hardware. It has a TI DSP on board, and this DSP is directly programmed from Workbench. And the Workbench model-based design allows you to program this DSP without having to know anything about the device, nor having to do any C programming. And this board also has an FPGA on board, simply to convert the gate signals. Since the DSP cannot drive 24 gate signals, we have an FPGA on board to convert the duty cycles to drive 24 gate signals. And we have an onboard encoder to measure the speed and ADCs to measure the currents and the voltages. So this is the overall hardware of a 6 kilowatt direct 3-level matrix converter. And this is the view of every single leg of the matrix converter that contains 4 bidirectional switches. This is the overall model direct 3-level matrix converter controller algorithm implemented using Workbench. And there are multiple layers to it with more and more complexity within each layer to generate the switching pulses to drive this matrix converter. And all of this can be easily translated by Workbench into C program automatically and programmed into the DSP and drive the matrix converter. And the measured data can be logged back in Workbench as well. Here are the results of the matrix converter that's obtained from a scope just to get a finer resolution. On the left, you see the input voltage and the three-phase input currents. And at the right, you see the balanced three-phase voltage across the neutral point clamp capacitors and the input current. The bottom left shows the three-phase output currents, and on the bottom right shows the switched line-to-line output voltage of the matrix converter. This slide shows the three-level operation of the matrix converter. On the left, you see the input current, and on the right, you see the output line-to-line voltages. And all of this is implemented using the Workbench software and the controller board that was shown earlier. There are many other exciting projects in our lab that we use the Workbench software as well as the Workbench controller. And Professor Mohan would talk in more detail about some of the interesting projects that we are working on.
Okay, so then I'll say that what we are doing before 2017 here, see this development started, power electronics and drives lab development started almost 20 years ago. And, about 109 US universities have acquired it, okay, these laboratories here. So this board here is for the basic power electronics lab, which we were teaching at undergraduate level. And then this board here is for electric drives lab, which was also at the undergraduate level here. Okay, and in doing so, we were using this MATLAB, for simulation, and then DSpace, which is a rapid prototyping tool, and then we had this 3-inverter board, for controlling the motors here. So that was the procedure up until spring of 2017, and so the difference between what we are doing and what we are doing now is somewhat listed here. You can see the academic and the non-academic costs of these things here. For MATLAB, 7,000 or 20,000, more than 20,000 for non-academic. Then for DSpace, it costs roughly 6,000 for academic purposes and about 20,000 for non-academic. And then the inverter board is the same, okay? And so you see here that the total was about 20,000, more than 20,000 for academic purposes and more than 47,000 for non-academic purposes. So that's where I think, our effort has been to make them as low cost as possible. So now, starting in spring of 2018, we are using this in-house design simulation code. It's called Sciamble Workbench over here. And then we have designed a very high density 3-inverter power board, which is over here. Okay, and some details of this electric drives laboratory are shown here. It can fit in this box over here. So you have this 3-inverter board. This box here containing this 3-inverter board and the controller and the electric machines that are used for the experiment, and they all fit here inside this box here. And then some of the 3-inverter specs are given here. I'll not go into the details, but you can see that this is what we are using at the moment. Okay, and the capabilities here are that it can control up to 3 PMAC and our induction machines simultaneously, and it's designed to be able to control doubly-fed induction generator. And some of the experiments that we can do in the basic drives lab, which is taught at the senior level. Some graduate students take it too. And so these are the experiments that are listed here. Again, I will not read these experiments. And when it comes to advanced drives lab, it's at the graduate level, but some qualified seniors do take it, okay? So in the past, using the older laboratory, we were never able to do these advanced vector controlled type experiments, but all these experiments are not now possible, and we have been teaching this lab. So the number here is EE 5707, okay? Where the number here is EE 4703. I'm sorry, right here. Okay, not that it means anything to anybody outside the University of Minnesota, but I will mention that. So now we have also developed this wide bandgap based digitally controlled power electronics lab, and so in this laboratory we can do a lot more experiments than we were able to do before. So again, here's a list of experiments that we can do. You know, only a small fraction of these we could do in the past. So these are all digitally controlled, just like the electric drives lab here. And there's a low-cost general-purpose prototyping platform that Siddharth has developed. And then we are really hoping to have a emulated power systems lab. So this is under development. It's a work in progress. And so what we are hoping is that we can actually develop a 5-node microgrid, for example. It doesn't have to be microgrid. It could be emulation of, you know, some electrical system with certain nodes, some representing sources, some representing loads. But the idea here is that each of these sources and each of these loads are represented on one card over here, and the details of that card are shown here. And similarly, you know, something else, for example, this may be a you know, emulated grid connected PV system, and this could be some kind of a power system grid over here, where this power is being fed from the PV to the grid. So what we are hoping that each of these cards would be, you know, $300 or $400, maybe $500 a piece, and if you have 5 of them, you know, this whole thing would be like $2,500 to $3,000. So basically, you can have a desktop. Microgrid for, let's say, under $3,000, and then you can, you know, connect many of these. We don't know how many. Theoretically, it's any number, but practically we don't know at this stage. But you can connect many of these together. So not just 5 nodes, you could have 50 nodes. Okay, so even if you were to do that, the cost would be, you know, 3,000 times 10, that's 30,000. So you can all have it on tabletop, so to speak. So that's what we are aiming at. And here are the list of experiments that we can do. And again, I will not read them. So I'd like to finish by acknowledging that we are greatly indebted to 2 grants that we have received from Office of Naval Research. One of them is this, that allowed us to develop many of the courses that I talked to you about. And the second one, which is ongoing, is to developing these extremely low-cost laboratories. And they are, you know, digitally controlled, and they use, you know, these wide bandgap devices. And I'll be remiss in not saying that these are remotely controlled. Okay, so at least some of them already are, and all of them we are hoping that they will be remotely controlled. So when this COVID-19 hit in the middle of the spring semester, there was no interruption, because of course before that we were having these face-to-face laboratories, but as soon as we were you know, not allowed to go into the laboratories, we immediately went to you know, teaching them remotely. And so there was no interruption. And I may say that when it comes to cost, by teaching them remotely, we can further reduce the cost by a factor of 5. So let's assume that you have, you know, 10 stations, okay? I'm sorry, make it 5. Maybe you have 5 stations, 2 students per station. So you have 5, you know, experiment stations. So you have to buy 5 sets, right? 5 sets when you have face-to-face. But if you're having, if students are accessing them remotely online, then you just need one setup, right? And you know, the TA or the instructor sets up the experiment for that week, and then there's a sign-up sheet where students reserve a time slot. So, you know, for 7 days, and students work odd hours of the day, very early in the morning to very late at night. So, you know, there are plenty of hours in 7 days. And so for 30 or 40 student enrollment in a lab, we just need one setup. So imagine that you can set up the entire drives lab for under $3,000, okay? So that's the benefit of having these remotely controlled through the internet. And so having done all this development, the next question is that how are these laboratories going to be available? Okay, and that's where I'd like to mention that there is this Sciamble Corporation, Sciamble Corp, and it's a University of Minnesota startup. So these experiments are available through Sciamble. You just need to go to their website. And again, Siddharth is the founder of this company, and any information that you need, you can contact him. So this is all I have to say. Thank you so much for allowing me to talk to you. And if there are any questions or comments, both Siddharth and I welcome them.